Welcome to Lab 3. This lab is about multiplexers. A multiplexer is a very useful building block in logic circuits. So in today's lab, we are going to see what is a multiplexer, how you can build one using basic gates, and how to model these multiplexers in VHDL. Okay. And then we are also going to study some features of VHDL that we have not seen before. So we are going to see conditional signal assignment and selected signal assignment. These two ways of assigning values to signals. Okay. And the exercise for today's lab is going to be designing a 4x1 multiplexer. So let's begin. So the word multiplex in common English implies a many to one relationship. For example, a movie multiplex or time multiplexing and so on. So in the context of logic circuits, a multiplexer is a circuit that allows you to multiplex many signals onto one signal. Okay, so let's take an example of a simple 2x1 multiplexer. It has 2 bit inputs, A a single bit and B another bit, and it has a select line. If the value of the select line is 0, then there is a connection from A to Y. So Y takes the value of A, whatever it is. If A is 1, Y is 1, A is 0, Y is 0. Whereas if select is 1, then Y takes the value of P. So that is the behavior of the multiplexer. Okay, so it acts like a simple switch, a two-way switch, which could either be connected this way or this way depending on the value of the select input. That's the behavior of a simple 2x1 multiplexer. Note that this is a typical symbol. This wedge shaped symbol is used to denote multiplexer. Later on, we are also going to study a circuit called a demultiplexer, which does the opposite. It takes a single input and depending on the select line, it can send it out on one of these signals, right? So this is a demultiplexer, which we will see in the later examples, and it has an opposite symbol. So this wedge-shaped symbol is used to indicate a multiplexer, and we also usually write how many inputs and how many outputs in this manner. So 2x1 multiplexer. Okay, so let's see how we can design this logic circuit, the logic circuit to do this. Now the obvious way is to build a truth table. So we have A, B and select. When select is 0, Y equals A, whatever it is. So when select is 0 and A is 0, Y is 0. Similarly, when select is 0 and A is 1, then Y is 1. Okay. When select is 1, then Y is equal to B. So select is 1, so Y is same as B. Select is 1 here, so Y is same as B, and so on. So we build a truth table, right? And now we need to derive an expression for Y in terms of A, B and select. So take a moment to think about this. Take a moment to think about what this would be. Okay. Now, either you can arrive at the logic expression and then build a circuit, or you can just think from first principles. Let's do that. Let's think from first principles and build a circuit for that. So, okay. So select can be 1 or 0. So let's see. This is select. You have the select line, and you have the select line inverted. Okay. So when the select line is 0, we AND it with the input A, and when select line is 1, we AND it with the input B. We OR these together, and this is Y. Let's see if we just draw a better diagram. So we have, okay, we have A, select bar, we have B and select. Let's be convinced that this circuit indeed performs the multiplexing. If select is 0, then this is 0 here, so this AND gate is automatically output is 0. Okay, and this is not going to affect the output. This is 0. The output will be dependent only on this. So since select is 0, select bar is 1. So now the output of this gate depends on A. It will be equal to A because this is A and 1. So this is going to be A. This is A or 0. So this is still going to be A. So when select is 0, Y is equal to A. Now let's try when select is equal to 1. When select is equal to 1, this is 0. So this is 0. Select is equal to 1. So B and 1 is B. B or 0 is B. So Y is equal to B. So indeed, when select is equal to 0, Y is equal to A. Otherwise, Y is equal to B. So this simple circuit is indeed working as a 2x1 mux. So your first exercise is now to develop the logic for a 4x1 mux. Okay, you have a multiplexer that selects 1 out of 4 inputs and assigns it to Y. Since you want to select 1 out of these 4, you need 2 bits for the select line. So if the select line has values 0, 0, then A is connected to Y, and 0, 1, 1, 0, and so on. Okay, so depending on the value of the select lines, one of them should be connected to Y. So the exercise is to build a logic description for the circuit. So note that A, B, C, D are each 1 bit. Y is also 1 bit. It's only select line which is 2 bits. Okay, and you are asked to model this using VHDL using a structural description. That means describe it as an interconnection of simpler and, or, and not components. So describe these and, or, not entities. Okay, derive the logic expression and a simple circuit diagram for this, and build this mux. You are asked to use the same port names as given in this interface diagram for the mux. Okay, and the select line should be of type standard logic vector. All the other inputs should be of the type standard logic. They are 1 bit each. Similarly, Y is also of type standard logic. Okay, and you are also asked to write an appropriate test bench for this circuit. The test bench should preferably allow you to observe the output for all possible input combinations. Okay, so that's the first question. So I hope that you have understood the design of a simple mux. Now coming back to this mux, this is a very useful circuit, right? Now if you can have, instead of 1 bit, let's say this is a 8-bit bus A, B, and this is a 8-bit output Y. How many select lines are required? It's still going to be 1 bit, because depending on the value of the select bit, either all of these 8 bits of A are connected to the 8 bits of Y, or all of these 8 bits of B are connected to the 8 bits of Y. So it's either this way or this way. So there are only 2 values on this required. So S has to be just a single bit. So this is a very useful circuit or useful building block in many circuits. For example, let's say to this Y you could have connected an adder circuit, right? So, and the other something else. So now there could be a many to one mux. For example, there could be a 4 to 1 mux, and each of these 4 could be connected to the registers of your processor. So using this, you control which 2 registers are added. There is one more for the second operand. Let's say 1 more mux. So these are also connected to the processor registers. So if you have many processor registers, for example R1, R2 and so on, just by controlling the select lines of the 2 multiplexers, you can determine which of these registers actually get added and produce the result, right? So this kind of a thinking, okay, that you have some circuit, you have many sources, you have a mux, then you have some other circuit, you have another mux, another source. This could go to many other places and so on. So this is a demultiplexer and so on. This kind of thinking, okay, it's like thinking like a traffic police. You're just kind of directing where the data should flow from, right? You're controlling, using these select lines, you're controlling the flow of data. So for this mux, you're controlling whether this is connected here or here and so on. So this kind of thinking is called data flow style. Data flow style. Data flow style of thinking or modeling circuits. Okay. So far we saw the structural kind of style for writing VHDL models. Then we saw that you can write higher level models using behavioral code. And now we are seeing an example where you can write data flow style of code using multiplexers. So now let's move on. So we are going to study some new features of VHDL. So coming back to this concurrent signal assignment. So think about what is exactly a difference between a port and a signal. This was not explicitly described in the past lecture. A port refers to an interface of the entity, the outputs or the inputs or the in-out ports, right? It refers to the interface of the entity. A port can only be of these types. It has modes. It can be of in type or out type or in-out. For example, an in port cannot be written to, an out port cannot be read, and so on. There are some restrictions. So port defines the interface of the entity. How does this entity interact with the outside world? It can only interact with the outside world in certain well-defined ways. That is, this entity changes its output, or that is, it's activated only when its inputs change. Okay? And when its input values change, this entity will update its output values. So that's ports. So what is a signal? In all the examples before, we saw signal as something being internal to the entity, and that's right. A signal is something that is within the entity. It could be used for intermediate signal values. For example, look at this circuit. So this A, B and A, B, C and Y could be the ports of this entity. But you may need to connect the output of this NOT gate to this AND gate, so you use a signal in between. You may declare two signals. So signal is something internal to this entity that the outside world cannot see. So what does a signal correspond to in hardware? Most of the time the signal just corresponds to a wire. You can imagine it like a wire. Okay, and something is assigning a value to it. So this could be a gate, for example. Something is driving a value on this signal, and something may be reading a value from the signal as an input, for example. So this is a signal. Okay, that is one example, but in some other cases a signal could actually correspond to a memory element, a flip-flop. Okay, for example a D flip-flop. So that can happen when you write a description in such a way that you assign some value to the signal, and then under certain input combinations the value should remain unchanged. Okay, that means on some input combinations the value of the signal is updated, but on some combinations the value remains unchanged. If that is how you describe the code, then how do you store a value on a wire? You can't store a value on a physical wire, right? So it will actually imply a memory element, a flip-flop or a latch or something. So we will see these memory elements later on in the course. Right now just think of a signal as a wire. It's sufficient for our examples right now. So that's the difference between a port and a signal. A signal is internal to an entity, a port is its interface. Okay, so coming back to concurrent signal assignments, remember we discussed that VHDL statements are concurrent, right? So here is the circuit. The input A is inverted to create S1. S1 and B is ANDed together as S2. S2 is ORed with C and Y. So which of the following descriptions is correct? This one or this one? So if you notice, in the first description they occur in the same order from left to right, the signal assignments, whereas in this one they are not, in some other order, right? But since I said that these are concurrent statements, these describe things that exist at the same time. So if you write the VHDL description in this manner versus in this manner, is the same circuit. You are describing the same circuit, the same thing. If you simulate these two in VHDL, you will get the same result. Okay, they describe the same thing. So they are the same. The order in which they occur doesn't matter because they are not executed one after the other. These statements are all concurrent. Okay. So now this signal assignment is the simplest form of signal assignment, right? You have the signal name, for example S, then the signal assignment symbol and some expression. This expression could be a constant, or it could be the name of another signal or a port, or it could be an expression, for example A and B, and so on. So AND is an operator and it's a keyword in VHDL. For example, similarly NOT, AND, or XOR, they are all keywords. Okay? So this is a signal name, assignment operator and an expression. Okay. So this is a simple concurrent signal assignment statement. Let's see some other kinds of signal assignment statements. So we have a statement called a conditional signal assignment. So you can remember this is the statement that includes a when. Okay. So this reads like this in the general form. Signal is assigned some value when some condition, else some other value when some condition, else, and so on. And finally this is the last, this is the default. So this is when none of the other conditions are met. So let's see a concrete example. Y is assigned A when some condition, for example S is 0 or S is 1 and B is B, something like that. Else it is assigned a value 0 when some other condition. So this is a not equal to symbol. This is equal to and this is not equal to. Okay, these are the two symbols in VHDL. So if this condition is met, then Y is assigned A. Else if this condition is met, then Y is assigned 0. Else if this condition is met, if none of these conditions are met, then this is the value by default which is assigned to Y. Okay, so this is the default case. So this is an example. This may remind you of the if-else construct in C++. So if condition, then do something, else do something. So in this case, if something, assign a particular value, else assign a particular value, and so on. Okay. So the conditions are evaluated from here to here. Okay. So multiple conditions might be satisfied. For example, A is assigned 1 when A equal to 1 and B equal to 1. Else it is assigned 0 when A equal to 1. So now A equal to 1 and B equal to 1 and A equal to 1. So this is a subset, this is the subset of this condition, but this is checked first. So they are evaluated in this order, okay, in this order of priority. It's still a concurrent signal assignment. It's not sequential, but these conditions are checked one by one. Okay, the first condition to be satisfied that value is assigned. Okay. Now, is this a concurrent statement? It is. Okay, it is, because it is concurrent relative to all the other statements that may be there in the description. So let's see an example of this used for modeling a multiplexer. So here is a 4x1 multiplexer. Now this is not a structural description, this is a data flow style description. So the 4x1 mux has 4 inputs, A, B, C and D of type standard logic. They are each 1 bit. It has a select input. Since you want to select from one among 4, you need 2 bits. So we have S is a standard logic vector 1 down to 0 and Y is the output. And this is the example of the conditional signal assignment statement. Y is assigned A when condition, else B when condition, else C when condition, else D. So when none of these are met, this is the default. Okay. So notice that this covers all possible values of S, but it is usually a good idea to explicitly list down all the possible options and then in addition have a default option. This is just to avoid human errors in missing out a particular value. If you miss out a particular value, you might sometimes lead to a memory element. Remember, right now Y is just a wire, because for any combination of S, Y is some function of the inputs for any combination of S. Okay, but if there was some case missed out here, then it would imply that Y should not change at all, right? None of these conditions is met, then Y would not change, it should remember its old value. Then Y would have to be a flip-flop. So just to avoid that error, make sure that all possible conditions are covered. You don't miss out any condition. Okay? Or you just have this default thing. So when none of these conditions are met, there is this default option which is taken. So this is an example of creating a mux using a conditional signal assignment. Notice that this description is much cleaner compared to actually having a logic circuit, but it's a higher level description. Okay, this can be translated into a logic circuit automatically by synthesis tools. We will now see another type of signal assignment statement. Okay, this is called a selected signal assignment. Okay, so this will remind you of the case construct in C or C++ if you're familiar with it. The format of this looks like this: with expression select, the signal is assigned some value, something, when choice. So that means when this expression is equal to this value, and something else when another choice, and so on. So this is the format. So let's see an example. With A XOR B select, Y is assigned 1 when 1 and C when others. Let's see, C is some other signal. So what does this mean? So A XOR B is evaluated, okay, and if it is 1, that is this, then what is done? Y is assigned this value. Else, that is this others, Y is assigned C. So it's like a case statement. So you don't have multiple expressions, you have only one expression, and you have different values that expression could take. These are the values of expression. So if the expression takes this value, you assign this. If the expression takes this value, you assign this, and so on. Okay, so that's the format of the selected signal assignment statement. Okay, so here is an example of the same multiplexer built using the selected signal assignment. So this is same. So with S select, Y is assigned A when S is equal to 0, 0. is B when 0, 1, and so on. So notice that the format is slightly different. So the two kinds of signal assignment may look very similar. So let's compare the two side by side. So the same mux example. So here is a conditional assignment. We don't have any expression in the beginning. We just have y is assigned A when some condition, else B when some other condition, when C when some other conditions, and so on. All these conditions can be different. They don't have to be about S. They can have involve some other signals also. These can be different conditions. Okay. Whereas, so this reminds one of if else in C++, right? And whereas the other one is a reminder of the case construct in C++. It looks like this. With S select. So first you tell what is the expression to be evaluated and what are the values that expression can take. So it could take any of these values. If it takes each of these values, what is the value to be assigned to the target? So y is A when the value is 0, 0, and so on. So both can be used for describing things like multiplexers, decoders, and so on. Okay, so you use one whichever is appropriate, and pay attention to the syntactical aspects of it. There is only a semicolon in the end. Here there is a comma after each case. Okay, so this is a conditional assignment when else. This is a selected assignment with S select and so on. So an architecture described using these two constructs solely is sometimes referred to as data flow style description. So let's go to the second exercise. You are asked to build a MUX, a 4x1 multiplexer, using data flow style descriptions, okay, with this interface. So it's a 4x1 multiplexer. Each input is now a 8-bit bus, okay, and the output is also 8-bit. The select lines is still 2 bits because you are selecting one out of 4 options. So A, if select is 0, 0, then A is connected to Y. All the bits of A are connected to the corresponding bits of Y. If S is 0, 1, all bits of B are connected to the corresponding bits of Y, and so on. Okay. So you are first required to write this entity description and declare the ports. They should all be of type standard logic vector. Okay. And then you are asked to write 2 separate architectures for the same entity. One architecture that uses only conditional assignments and another architecture that achieves the same job using only selected assignments. Okay. After you describe these architectures, you are required to write an appropriate test bench. So think about a strategy for testing this. How would you try out all possible input combinations? Think about how many possible input combinations are there for all the inputs. Okay. And you are required to describe your testing strategy via comments in the test bench code. So write an appropriate test bench using all the features of VHDL that you know of. Okay. And validate both the architectures using simulation. Check if the multiplexer works as expected. So Y should reflect exactly the one of these inputs as specified by the select lines. And submit all of the code including the entity, the 2 architectures and the test bench in this single VHDL file. So that's the exercise. Okay. So that's it for the third lab. Bye.